Good morning and welcome everybody. I'm really glad to welcome you to this our last training activity that will be dedicated to the collaborative robotics in industrial implementation towards more flexible and integrated factories. So after our last four training activities in which we had a lot of technical description of what we have been able to develop in all the different modules that have been carried out. Now we have a slightly different focus, and we will see how we will be able to implement all of these technical aspects in an industrial environment. So here you have a brief overview of the agenda after the introduction of the project and a first explanation on how you have to deal with the industrial environment when we want to implement human-robot collaboration systems. Then we will move to the description of the four different industrial environments in which we had our use cases. And we will just finalizing our session with the question and answer slot. Just a few administrative suggestions. So the question and answer slot will be at the end of the session, and you have a dedicated box in the GoToWebinar tool. So please drop your question in this box, and at the end of the session, we will just read them to the speakers. The presentation will last among 15 and 20 minutes. And after each of them, you will also get a brief self-assessment questionnaire just to keep your attention alive during the training, and also a questionnaire about if you like the training. Today we have a lot of speakers. First of all, myself as a project coordinator, then Francesca Canale, project engineer STAM, Michael Anagasasti, electronic engineer in Goldsberg, Dionysis Andronas, research engineer at LMS, Gerard Guerrero from SEAT, also project engineer, Pier Vincenzo Tavormina, industrial automation engineer from Cembre, Andrea Scala, technician from Cembre, Jaume Altesa, R&D engineer from Alstom, Giuseppe Fogliazza, director of MCE from MCM, and Filippo Parma, mechanical engineer from NCM. So just a few words about Sharework project. The project is a 4-year project that received 7.3 million fundings, and the consortium is composed by 15 partners coming from 6 different countries. So, but which is the need behind the project? Currently, there are 2 million robots in the world, but just 5,000 units are dedicated to collaborative tasks. And due to the boost of Industry 4.0, the cobots market is expected to reach 3.7 million by 2023. Sharework has different objectives. The first one is to design an evolving knowledge base and semantic environment, then to develop a human-aware dynamic task planning and scheduler system, and a robot offline and real-time motion planner. Everything is possible thanks to a multimodal human-robot communication system, and obviously we are also developing methods and to overcome all the human-related barriers and concerns that can arise in this field. Regarding the methodology, our project, the technical activities have been divided in 4 different main areas. The first one is perception. Thanks to different kind of sensors, the system are capable of recognizing the environment and also the presence of the humans and the operators. The second area is dedicated to the motion planning. Thanks to our models, the robot is able to recognize what the operators are performing, so which are the tasks, and in this way organizing himself to have a dynamic planning and a schedule of the collaborative task. We also obviously dedicate a part to safety and security, especially we have a module dedicated to the safety for humans. Then we have one dedicated to data security. We have the continuous evaluation of ergonomics. And finally, we have the operator training to augmented reality. And finally, as I said before, everything is possible just thanks to the human communication among robots and operators. So in our project, we have 4 different use cases. The first one is dedicated to the railway sector, led by Alstom. Then we have the metal sector, in which we have Cembre. Capital goods, in which today we will be represented by Goetzper, and the automotive one by SEAT. So now we are almost at the end of the project. The project will finalize in October. So we are already in the final phase of the implementation. And this is why we are here today. So today we are going to see how all the technical activities that have been performed during this 3 years and a half will be integrated directly in the industry. So now I'm going to give the floor to our project video, and thanks a lot for being here today. So I hope you enjoy our training session.
In the age of Industry 4.0, the industrial landscape is being transformed by technologies, allowing factories to be more connected and automated. Industrial robots have evolved considerably during the past decades, improving in productivity, efficiency, and security. But they are still not flexible enough to coexist and share production tasks with humans. The EU-funded project Sharework aims to provide robots with the necessary intelligence to safely work with humans without the need of protective barriers. Thanks to Sharework, industrial collaborative robots will be capable of understanding the environment and human behavior. A solution to boost process productivity and improve workers' well-being with better ergonomics and safety at the workplace. The resulting technology will be validated in the assembly areas of 4 different companies of the automotive, railway, metal, and capital goods manufacturing industries to evaluate its applicability in different industrial processes. A new smart robotics system for fostering industrial competitiveness in Europe. To find out more about Sharework, visit sharework-project.eu or find us on Twitter.
Okay, so we will start our first presentation that will be given by Francesca Canale. Francesca received her master's degree in robotics engineer at the University of Genoa in 2020. During her studies, she was involved in several projects where she acquired the general knowledge of multiple aspects of robotics. She joined STAM, the robotics and mechatronic team, in 2020. And during this year, she has been handling all the technical aspects of research and development project in the field of robotics, manufacturing, and automation solution. So today she is going to give us a presentation about human collaborative system in industrial environments.
Thank you, Simona, and good morning, everybody. So today I'm gonna give a presentation, and I'm starting with some basic concept about human-robot collaboration. For example, which are the different levels of interaction between human and robot, and which are the main safety standards in collaborative environment. Then I'm going to present how the topic of human-robot collaboration has been addressed in the Sharework project. And finally, I'm giving some conclusions. So starting from some basic concept about human-robot collaboration, we can say that generally we can divide the manufacturing process into different categories depending on the level of automation. We can start from a level of zero automation, that is the manual manufacture, and arrive to a level of fully automated production lines. In the first case, the main character is the human operator, while in the second case, the work is completely carried out by robots or automatic machines. Each different type of manufacturing have different features depending on the skills of human on one side and of robots on the other side. So, for example, manual manufacture is flexible since humans are able to adapt to changes, for example, in the product that they are manufacturing. Then human manufacture has dexterity, since human hands are able to perform complex tasks and also to manipulate easily different types of objects. Then, of course, there is the decision-making capability of humans. Regarding some drawbacks of manual manufacture, we have that human can make errors, and then the health risk of operators, mostly related, for example, to ergonomics or to performing heavy tasks. Regarding instead the full automation, we have that the advantages are that the increased speed and quality of the products due to the introduction of robots. Regarding the cost, we have that robots are cheaper than humans, but they require a high initial investment. Another drawback can be the limited adaptability of robotic solutions that are often tailor-made on specific process and cannot be adapted to changes. In this context, human-robot collaboration is born to fill the gap between these two different kinds of manufacturing process. But what is human-robot collaboration? We can say that human-robot collaboration is when human and the robots share their workspace. The robot helps the human operator in the most uncomfortable, non-ergonomics, and dangerous task, while the human operator works as a supervisor and in all the tasks which require human skills. So robot and human can work together, and in this way it is possible to integrate the advantages of both manual manufacture and fully automated production lines. Each one brings their own features to the collaborative process. So the robot aims to increase the efficiency and the productivity, since robots are really fast and very accurate. And while human brings flexibility, dexterity, and cognitive capabilities to the process. Going into more details, there are 5 different ways of interaction between human and the robot, and they depend on how they share their workspace. So we can start from fenced robot, where there is a fence between separating the workspace of the robot and of the human. In this case, it is not possible any contact between them. The second level is coexistence. In this case, human and robot have separate workspace, which never overlap. So they work in parallel in their respective workspace without any kind of interaction. Then there is a synchronized or sequential interaction. In this case, human and robot utilize a shared workspace, but at separate times. So the workspace is shared, but they work on the same product, not at the same time. Then there is cooperation, where human and robot work on their own product in a same workspace. So the workspace is the same, the time is the same, but they are working on different products. And finally, there is collaboration, which is the last level. And in this case, human and robot work simultaneously on the same workspace, on the same product. So in this case, time, product, and workspace are the same. When human and robot share their workspace, we have the safety issues become one of the most important aspects. Because the collaborative environment could be extremely dangerous for human operators due to possible unpredictable contact with between a robot and human that can cause severe injuries to the human operator. For this reason, safety is one of the top priorities. In the years, some safety guidelines have been defined for collaborative environments, and they define that at least one of the 4 safety modes highlighted in these slides have to be implemented in collaborative scenarios. So, the first mode is safety rated monitored stop. In this case, the human and the robot can work separately in their own workspace, and if they are separate, the robot can work at full speed and there is no need for a fence. But if the human enters the workspace of the robot, then the robot should perform a safety rated monitored stop. So it should be immediately stopped. There is no need for a fence, but some safety sensor need to be integrated to detect when the human is entering the workspace of the robot. The second modality, safety modality, is hand guiding. In this case, the operator can control the motion of the robot via an hand guiding device. When they are working in separate workspace, the robot can work at full speed, but when the human enters the workspace of the robot should be stopped via a safety rated monitored stop. And once it is not moving, then the operator can proceed by controlling the motion of the robot via the hand guiding device. The third safety mode is speed and separation monitoring. In this case, human and robot can work in the same workspace, but the speed of the robot should be adjusted according to the position of the operator, according to the distance between operator and the robot. If they become too close, then the robot should stop. The last mode is power and force limiting. In this case, physical contact between human and robot is possible, but in case of contact, the forces applied by the robot to the human body should be below a threshold, which has been defined during risk assessment. This mode is only possible with collaborative robots, which have integrated force and torque sensors. Collaborative scenarios should include at least one of these 4 safety modes. One last aspect that I want to introduce today about human-robot collaboration is our collaborative robots. Collaborative robots, or simply cobots, are robots which have been specifically designed to work with human operators. They are characterized by technologies which allow to avoid any injuries in case of collision with the human operators. Some of these technologies are, for example, force feedback, collision detection, or even soft and round edges of the robot. If we want to compare robot and cobots, we can say that robots are ideal for large companies producing large batches of the same product for years, while cobots are designed to work with a low volume and high mixed production, where the robot is often reused in different processes. Then robots have complex deployment because they require extensive programming knowledge to be set up, while cobots are easy to set up and even by users which don't have extensive knowledge in robot programming. Then robots are not safe without protection, so they require safety fence to keep the human worker outside of the workspace of the robot, while cobots are things to work with humans, so they don't require fences and the human is safe with them. Then in robots, the focus is on the robot that repeats the same movement with the same tool for years, and it is integrated in a specific process, while in cobots, the focus is on the tooling. So the robot is only the foundation where different types of tool can be integrated to complete a different task. And to conclude, cobots are cheaper than robots, and so robots require large investment with a longer return of investment. So now I can present how these different topics have been addressed in the Sharework project. So the Sharework project aims to create an innovative industrial work environment characterized by the necessary intelligence for the effective adoption of human-robot collaboration without fences. The system is modular and is composed of 14 different modules developed by the different partners of this project. And the modules can be grouped into different categories that are workspace cognition, task and motion planning, human safety, and interfaces for effective collaboration. These different modules interact with each other and with the surrounding environment, like, for example, with cameras, with interfaces, or with the robot. And in all these categories, take into account the different aspects of human-robot collaboration. So going deeper in each category of modules, the first one is the workspace cognition. And the purpose of this category is to generate information from the surrounding environment and from the data captured by cameras and other sensors. So we want the system to be aware of the surrounding environment and to understand what the operator, where the operator is and what the operator is doing. So we have a module that allows to compute the real-time trajectory of the operators, that is the human tracking module. Then we have a module that allows to identify which task the operator is carrying out, that is the human task identification. And for example, you can see in the picture on the bottom that the system is able to understand that the operator is spreading silicon. Then we have a module that is environment cognition that allows to understand, to detect, to recognize objects inside the workspace, for example, working tools. And we have the primitives learning module, which allows to recognize some gestures that the operator is doing to maybe give commands to the system. And all these modules and all the information captured by these modules are used to update the knowledge base of the system, which represent the knowledge of the whole system. And it is updated in real time with the information captured and computed by the other modules. The second category is the task and motion planning. This category, these modules, takes in input the information computed by the workspace cognition modules, and these three modules allow to plan and execute safe robotic tasks. So there is a task planner that plans the optimal task to be executed by the robot, and there is a human-aware motion planner which allows to execute the robotic trajectories. While executing the trajectory, the position of the human is always taken into account, so they are human-aware trajectories. The trajectory is made to avoid the human and also to adjust the speed of the robot depending on the position of the human operator. So if the distance between them become closer, then the speed of the robot is reduced. And then there is one last module that is robot motion planning based on learning from demonstration, which allows to build a predictive motion model to predict the motion of the humans. The third category is human safety, which is composed of 2 modules completely dedicated to the safety of operators. This module can be used in addition to the safe robot motion planner or instead of it. The safety system is composed of 2 different modules, a global safety and a local safety. The local safety consists in the introduction of safety sensors, like, for example, LiDAR sensor, to detect potential hazards in the environment, while the local safety system is necessary for the situation where the global sensors are included. If there was not a local safety system, the robot would need to stop each time the operator is inside the workspace of the robot, but the global sensors are included. In the video from this slide, you can see an example of the local safety system working, and you can see that the robot avoids the collision with the operator and it stops when it comes closer to the operator. The last category of modules address another fundamental topic of human-robot collaboration, that is the communication between human and robots. We are interested in the communication on both sides, so from the system to the operator, to visualize interesting information for the operator, so that the operator is aware of what the system is doing and of what the robot is doing. And then we are also interested in the communication from the operator to the system, so on the other direction, because the operator may want to give input, to give feedback or comments to the system. In Sharework, it is possible to integrate different types of devices, like interfaces for the communication between human and robots, like, for example, tablet or smartwatches or augmented reality glasses. And all these kind of device allow an effective communication between the Sharework, between the robotic system and the operator. So to conclude, we can say that in the last decade, many research efforts have been focused on human-robot collaboration, especially in industrial environments. The motivation or reason behind this is that human-robot collaboration is really attractive for industrial scenarios because it is characterized by the combination of complementary strengths of human and robotic skills that leads to more attractive work environments characterized by increased productivity, flexibility, and adaptability. However, the wide deployment of human-robot collaboration in industrial application is facing big challenges, and the safety of the human operator is always the first concern. Thank you very much.
Thanks a lot, Francesca, for the presentation. So you have seen which are the main challenges, but also the advantages of having collaborative robotics in the industry. So now we move to our first self-assessment questionnaire. So here you have how many levels of human-robot interaction exist? A, 3, B, 4, C, 5. Okay, I see that there's 36% of the attendees already replied. It seems that the answer is not so clear. We have an equal distribution among the three, almost. Let's see, we have still a few seconds more. Ten seconds more, if you want to give your answer here. Okay. So we can close the survey. So I suppose, Francesca, you can see the answer in the screen. Yeah, I mean, it seems that most of the attendees replied C, 5, but we have also other answers. So if you want to give us...
So the correct answer is 5, because there are 5 different levels of interaction between human and robots, which are fenced robots, coexistence, synchronized interaction, cooperation, and collaboration. So theoretically, these are 5 different ways that human and robot can interact between each other. So the correct answer was 5.
Okay, so thanks a lot. Okay, so now you have also another quick question to answer. So in the meanwhile, now we are going to move to the presentation that will be given by our industrial partners regarding the use case of Sharework project. So you will see much more in detail which are the real applications that we are developing. And our first presentation will be of Goisper. Goisper is one of the technological leader in the design, manufacturing, marketing of differential power transmission and automation solution. And our presentation will be led by Mikel Anagasasti. Hi, Mikel, how are you? He is an electronic engineer, and he got his degree in Sweden and in the Basque Country. He works at Goisberg company in the Basque Country too, in the R&D department since 2014. And today he's gonna speak us about the implementation of human robotics collaboration in their site. You should have the right to share the screen, Mikel.
Yes, can you see my screen? Can you see my screen?
I don't know, I cannot, but I don't know the others.
It has accepted.
Not yet.
Okay.
Now, okay, again.
Okay, now we can. Yes, thanks.
Yeah.
So, my name is Mikel Anasagasti. I am an electronics engineer. I work in Goisper Group. And I'm going to show you our use case, the implementation of collaborative robots for process automation while improving our operators' ergonomics. Well, this presentation will be focused in 4 points. We will start with a short overview of our company, Goisper. Then we will go through the use case. So I will introduce you the use case and we will see the main features of the use case. In the third step, we will focus on the Sharework solution that we will see the actual solution in Goisper and the proposed solution by Sharework. And we will finish with the main KPIs we have defined during the project to see what we are reaching in different features. So, Goisper, as Simona said, is located in the Basque Country in the north of Spain, and we're a middle-sized company with 170 employees and 40 million turnover per year. We have 2 main divisions, 2 main business. The main business is the power transmission components business, where we design and manufacture different components for industry, such as brakes, clutches, indexing tables, gearboxes, and turntables. Sharework project has been implemented in turntables assembly process. You see in the middle of the screen, that's the component we are going to assemble with Sharework. These components are used in different in different sectors, such as automotive, packaging, marine, but most of the turntables are used in automotive sector. And then there is another business for Goisper that I'm not going to go deeper because it is not related with Sharework, but we have another business related with spraying systems. So going through the use case, this is a short overview of it. As I told you, this is a turntable, the power transmission components we are manufacturing, and nowadays the assembly process is totally manual. So with Sharework, we will reach a collaborative area where the operator you see here working will be collaborating together with a cobot and a servo motor. We have defined two scenarios where we see that there is a need to improve. We need to improve in the ergonomics of the operators, as we will see later on. The first scenario is the bolt tightening scenario, where nowadays is done manually, but we will have a cobot help. And the second scenario is the quality control that nowadays is done by the operator alone, but in this case we will have the help of a servo motor. Well, the main features of the use case, as you see, are these 4 points. As Francesca said in her presentation, the main feature, the main objective is to have 100% safety. Safety must be assured all the time. But then we have also the real problematic that is, in our case, is the ergonomics of the operators. We have many sick leaves due to operators' pains, back pains, arm pains. So we want to reduce the physical effort of the operators in both scenarios. As you see here, these are some of the positions that the operators are doing during these works. And then we have some other features or objectives where, of course, if we can improve our quality and we can reduce our productivity, it's a good point for Goisper as well. But as I said before, the main point is safety, and then the problematic we have is the ergonomics. So this is the proposed solution. Nowadays, in the left side, we see how we work manually. The operator works with the tools and with a turntable for doing each assembly. At the right side, we have the proposed solution where the operator would have the collaboration of a cobot and a servo motor. In the same scenario, we can find different devices that are not main devices but are needed for Sharework, such as cameras, additional lights, screwdriver, the HMI for communication, some others. So let's go to both scenarios. As I said before, the first scenario is the bolts tightening. During the assembly of the turntable, several bolts must be screwed. So nowadays, the operator is doing it one by one, and it is not a high load task, but it's a very repetitive task that that finally it affects to the operators. So with Sharework, it has been proposed the next scenario here downstairs at the bottom of the right bottom of the screen. The operator will continue introducing the bolts in the holes, but it will be the cobot, the one responsible to detect. It will recognize if there is a bolt or not in the hole, and after recognizing it, if there is a bolt, it will introduce it and screw it with the correct torque. For sure, operator and cobot will be working in the same area. So if the operator is getting closer, the cobot will slow down, or even stop. As you see, there is a electric branch at the arm of the cobot that will be responsible to screw the bolts. Well, so as I said, there is a collaboration because they are working in the same area, the cobot and the operator. So it is very important to have some cameras to track the human all the time, to know where the human is, and to slow down, as I said before, if the human is entering in the cobot area. As I said in the last slide, the safety is the first, so no collisions is accepted. Well, if you go to the second scenario, the second scenario is based on the control of the internal components of the turntable. There are some internal components, cam followers, that are rotating inside these two windows. And it is very important to check how these followers are rolling. For that, nowadays, we're working in this way. The operator is turning the shaft, the input shaft, and meanwhile, using the mirror, the operator checks how these cam followers are rolling within the turntable. The turning of the shaft is very hard. We are talking about 120 Newton meters. That sometimes more, and it's a point that we want to remove from this activity. So for that, the idea was the operator to focus the operator only in the quality and the checking of the rolling. For that, we have inserted a servo motor because nowadays the cobots have not the enough torque to move this kind of shafts. And the idea is the operator and the servo motor to be working collaboratively. So there will be a communication between the operator and the servo motor, that it will be through gestures, and the servo motor will actuate according the gestures of the operator. Here we can see how the cameras are detecting human gestures. So, for example, if the operator is raising the right hand, the turntable will turn in one direction. If we raise the other hand, the left hand, the turntable will rotate in the other direction. And in this case, the operator is not moving any load, any high load. The operator is focused only in the quality inspection. Well, so these are the main KPIs. After seeing both scenarios, I'm going to mention only the main KPIs because there are many KPIs apart from this. But as I said before, main pillar of Sharework for us is safety, and we cannot accept any collision between human robot or robot and the environment with any other device. Then we have the ergonomics, that our problematic is totally due to ergonomics of the operator. So we want to reduce the repetitive loads. In the first scenario, it was the bolt tightening, from the 50% to the 25% of the cycle time, because the cobot will be the one that is screwing the bolts. In the second scenario, we will reduce the high load of turning the input shaft from 90% of the work that is doing now the operator to 0%, because the operator will not turn anymore the input shaft. And finally, we have another main KPI, but let's say that is in a secondary step. That is due to productivity. We want to reduce, if it's possible, the nowadays productivity. In the first scenario, we are looking for this cycle time, 60 seconds and 10 seconds per each bolt screwing. And for the quality inspection, nowadays we are doing this inspection, this task during 1 hour, 60 minutes, and we want to reduce it to 45 minutes. But as I said before, the main KPIs are the safety and ergonomics KPIs. So that's all from my side. Thank you very much.
Thanks a lot, Mikel, for the presentation. So here we have seen how collaborative can support tasks that are requiring both strength and precision. Now we move to our questionnaire. So here you have the question: what is the main problem that should be solved in both GOISPER scenarios? A, low productivity, B, bad ergonomics of operators, and C, too many issues due to bad quality. Okay, so the 50% of the attendees already replied. Okay, it seems that now we have a clear answer. Everybody replied that is bad ergonomics of the operator. Mikel, do you want to say something about that?
No, the answer is good. The correct answer is B, bad ergonomics of operators. That's right.
Okay, so really good that everybody was paying attention to your presentation. Now we move to the second survey. In the meanwhile, I would like to remind all of you that you can drop your question in the dedicated box, or also you can comment or raise your hand in the chat. If you want to ask something, Mikel, for the last session we have in the, at the end of the training session. So now we move to the second presentation of SEAT. There isn't much to say about them. You know, they are a car manufacturer that sell vehicles under SEAT and Cupra brands. And today for this presentation, we have two different speakers. We have Gerard Guerrero from SEAT that began his career in 2004. He has been dedicated to mechanical and hydraulic systems. And in 2016, he specialized in automation, PLCs, and process data analytics. This he joined the process engineer department of SEAT, and he is now participating to a Sharework project. This presentation will be also supported by Dionysis Andronas, that if you have been attending our other session, you know already. He holds a bachelor and a master in mechanical engineer and aeronautics from the University of Patras, and he works as a research engineer at the Robots Automation and Virtual Reality Manufacturing Group of laboratory for manufacturing system and automation in LMS. He has been managing different projects, European and also regional, like Versatile, Merging, and Sharework, that concern the design of collaborative workstation. They are currently both in SEAT because they are working on the demo site, and today they are going to present human-robot collaboration benefits during the assembly of a vehicle bodywork components. So I give you the floor, Gerard and Dionysus, and thanks for being here.
Thank you, Simona, and good morning, everyone. First of all, I just would like to give you an overview about our company in global terms of sales, employment, and investments. As you can see here, we are more than 14,000 employees here in Martorell. During 2021, SEAT and Cupra sold more than 470,000 vehicles in Europe, North and South America, and Asia. And our main and most important market by now is the first one, is Europe. Innovation, new technologies, as well as the environment are three of the most important pillars of our company, as you can see here. And next slide, please, Dionysus. Okay, SEAT are the only company that designs, develops, manufactures, markets, and sells cars in Spain. Part of the Volkswagen Group, it sells its vehicles under the SEAT and Cupra brands, while SEAT Mo is the business unit which covers urban mobility products and solutions. Currently, here in Martorell, we manufacture vehicles from SEAT, Cupra, and also Audi, and we can manufacture until 500,000 vehicles per year. Switch the slide. Okay. We decided to carry out the Sharework project in the painting area, as you can see here, and here you can see some characteristics about our facilities. And simply, I shall now give the floor to my colleague Dionysus Andronas from LMS. He will give you more details about the SEAT use case within this Sharework project.
Okay, thank you, Gerard. Well, the use case deals with the assembly and also the disassembly of body part components from vehicle chassis as they arrive at before the paint shop. So the operators have to pick parts from the storage area or the buffers and transfer and finally assemble them on the vehicle chassis that they are moving on the conveyor system. Those parts weigh approximately 15 kilograms, so we understand that this process for a complete shift, of course, emerges serious problems. For this scenario, we see that the operators are working on the hood, but also on the car doors, and also on the tailgate of each car. They may assemble those parts before they have their before we have the painting process, or they might disassemble those components from chassis that have already been painted, but defects have appeared and they need further processing. Summarizing this scenario, we can see that there are some ergonomic issues. The majority of the parts, as mentioned, weighs over 15 kilograms, with some of them weighing over 17 for some vehicle variants. For this, and this emerges serious ergonomic issues. So we want to improve working condition and also introduce automation for optimizing the process and also optimizing the well-being of the operators. So, a few words now about the proposed solution of what Sharework would like to bring in this concept. Here is an overview of the demonstrator that has already been implemented at LMS. We are using a high payload robot to handle the transportation of heavyweight components from the storage area to the chassis and vice versa. In the same time, we keep an operator in the loop because operators have flexibility, and also their cognitive skills are ideal for handling some of the challenges of this case, that are the low repeatability in the positioning of the chassis, and also the high number of variants in the same line. We have to mention that a huge challenge of this case is the assembly of those components to the chassis, the doors to the chassis, because we have to perform a dual pegging home process in parts whose relative position has a lot of variances. So we have developed a series within the project. In terms of hardware, we have developed specialized tools for this process. We have designed the effectors that they are sensory enhanced in order to support all of the functionalities that we are going to discuss in a few slides. And also they are able to handle the manipulation of variant components without any hardware modifications. Focusing now on the modules of Sharework, here is an overview of the module number 9, which is designed to provide smart solutions regarding the interaction of the human operators with the rest of the Sharework system. This multimodal interface consists of an augmented reality headset. We have a tablet interface, an Android tablet interface integrated on the robot, and we also are able to support other wearables such as smart watches, and introduce conventional HMIs like lights, LED strips, screens, monitors, and so forth. Those interfaces now offer a huge variety of available modalities, either for human system interaction or system human interaction. So depending the preferences and also the experience level of the operator, we can have instructions or robot information, safety notifications like trajectories of all safety zone arrangements that can be provided to the operator with different means, and also be customized to a huge extent in order to have a more personalized system. In this case also, we have implemented and tested the data security module of Sharework, which as a module aims on ensuring human safety in case of a detected cybersecurity threat. And for this case, we have also, sorry for the background noise, but we are at the factory. So in this case, we have also implemented the manual guidance. We have also implemented the manual guidance system that uses an optical sensor, and through a pitching gesture, the operator is able to seamlessly manipulate the robot and fine-tune the position in order to perform the pegging hole process that was described. We have also implemented the safety system that is based on Bill's safety eye with dynamic safety zone reconfiguration depending on the position of the robot and also the context of the current executed task. And now we have some videos of our experimental setup. Due to the timing, I will skip some of the details. Here we can see the robot being able to grasp the components. At the same time, the trajectory of the robot is visualized inside the operator field of view, and also the current safety zone configuration in order to avoid any hazard situation and also avoid the unexpected stops of the robot due to human intervention in cases where it shouldn't be. Here is the robot that is transferring the part. We may move on a little bit, and at this point we are able to see the operator with a pitching gesture to fine-tune the position of the robot in order to perform the dual packing hole process. So the operator optimizes the position and finally guides the component to its final position. When this operation ends, the operator performs some manual tasks like fastening those screws here, and augmented information is used for novice users and in order to support them during runtime operation. Here we also see how the safety zone configurations are dynamically updated. We can see the safety zones from the safety eye and also how they appear inside the operator field of view. The same process is repeated also for the second door, but I think it's more not worth it to show also the inverse process. So the inverse process involves the disassembly of the doors from vehicles that defects have been identified. So the operator uses the same modules to lift the doors and disassemble them from the hinges. The operator uses the interface for direct robot control. The robot, actually the door is manipulated away from the chassis, and as soon as the process ends, the robot then moves the component to the storage area, and the process is completed as well for the second part. All this information can be customized. Those features can be enabled or disabled depending the level of experience of the user. And these options aim to avoid excessive cognitive workload and also to create a more personalized interaction pipeline between the robot and the operator. A few words now about the industrial demonstrator and what we are currently working on. The principle is the same. We have a heavy payload robot. We have also a gripper that is equipped with a 3-axis force sensor, and also we have some perception systems in order to improve operator safety with the global safety module that Fraunhofer is working on. Here is the overview of the layout that we are working on currently. We have the vehicle chassis loaded on the conveyor, and the robot is responsible for transferring the parts from a storage area to the chassis, and the operator is only responsible for securing the hinges, both on the hood and also the door. So that's all from us. We are open for questions in the final Q&A session. Thank you very much, and sorry for the background noise.
Thanks to both Gerard and Dionysis. So I think that at least all the videos were pretty self-explanatory. So it's also really easy for people not from the sector to understand which are the advantages of these robots. So now we have also our quick survey. Here you have. What is the main challenge of the Envision solution in SEAT? A, symbiosis with high payload robot. B, interaction. C, hand guiding. D, training. E, A, B, and C. Now 45% of the audience already vote. Let's give 20 seconds more to see if we can reach the 100%. And thanks a lot for being with us today, that I know that you are hardly working on the final setup. So it's nice to see that everything would be most likely ready soon. And the next videos will be directly SEAT facilities. So, okay, I think we can close the survey, or also here we have 100% of the attendees that reply just one answer, the E, A, B, and C. So if you want to comment, I suppose that is right, but please go ahead.
Yep.
Yeah, it is correct.
Yes, the training within Sharework has been formalized and we have a framework that will be applied, that can be applied in all the cases. But for this, for the shared scenario, the hyperload robot is the main challenge, and also the technology of the hand guiding, let me say, is one of the trickiest parts.
Mm-hmm. Okay, then, so thanks a lot again for this presentation. And now I'm really glad to introduce another neighbor, Jaume Alteza from Alstom. Alstom develops and markets mobility solution for the railway sector that provides sustainable foundation for the future's transportation. And Jaume is an industrial engineer that has been working in Alstom here close to Barcelona for 20 years. He works on the manufacturing engineer department and in the innovation area, and he has experience with virtual reality, 3D printing, and he is working currently in Sharework project for new application of collaborative robotics. He is also giving us the presentation about their use case, uptaking a collaborative robotic system to improve train manufacturing process. Thanks a lot for being here, and I give you the floor.
Okay, thanks, Simona. Okay, as explained, we are the industrial case for railway. Okay, I will show you the presentation as other industrials, company overview, introduction of the use case, use it in Sharework, the motivation for automation, and proposed solution with Sharework modules and solutions from different partners. Okay, Alstom is a railway manufacturer. We developed signaling, after-sales, maintenance services. Here it focuses in new material manufacturing, new trains. In Alstom, there are several sites of manufacturing. We can build from tramway to high-speed trains to locomotive. And this project is based on the site of Barcelona, near Barcelona. And we are focused on mainly on urban trains and commuter trains today. Okay. Here it's how the factory is split, or the areas, the main areas of working, of type of works we can done. Okay, the main areas it's body shells, that we are experts in aluminium mainly and fittings. And these two main production lines are supplied with primary parts. It's machining area, I will say, an electrical workshop giving sub-assemblies, electrical sub-assemblies on these production lines. Here we'll see how it's made, more or less a simplified process of how we manufacture a train or rail car. Okay, we have aluminum profiles, machining aluminum profiles, welding, and we assemble different sub-assemblies of welding. And after we have a body shell, that it's a complete body shell. After we go to painting areas, after we have something like this, a car with already painted, and we go to assembly and fittings. And in this car, we put electrical equipments and mechanical equipments on under frame, on the roof, and inside. And we finish, we have an isolated car already finished. After this, we are doing a static testing for one car. We do it the train set composition. We make the coupling from several cars to have a train set. And with this, we do the dynamical testing, and we have a final train that you can deliver to the customer. This is a very simplified process, but to have an idea. Some point that we have to discuss to share when we discuss about our process, it's that we are the specificities compared to automotive and aeronautics. Sometimes railway is a little bit different, and this is the explanation how we consider we are different. Sometimes it's good, sometimes it's bad. Okay, but Here we are slow serial batches in general. The approaches could be 25, 40 trains. Okay. When we launch manufacturing, we have no freeze design. We are doing modifications during the advance of the process. We are not doing prototypes at the beginning of the process. We are in big assembly tolerances, around millimeters in all the assemblies. The product lifetime, you need to ensure a lifetime of 30 years. That it's quite a lot compared to other markets. Well, focus on cost, it can be shared with other markets, but it's a high level of competition, especially in urban, tramway and metro. And due to this, in general, it's low automation on the assembly lines. It can be sometimes a little bit manually, I will say. It's complex to make investments for low automation for these big assembly tolerances, low batches, things like this. In terms of automation too, its oppressor doesn't work in a fixed position. The workplace, it's big normally. It's low repeatability actions in general, and they have big range of movements that can be 20 meters working in a car. I would say the product, it's a workplace. Okay. And for this, well, on Sharework project, we choose this operation or this manufacturing assembly. It's one of most repetitive one, that it's for tramways, that it's the lateral frame, and it's, you can see it here. It's we build this lateral frame, lower part, upper part, and do door pillars like this, that it's aluminum profiles, and it's assembled by structural riveting. Okay. Here it's how it's done this process today manually. Okay, there is a clean surface, we press the profile, we make a mark, we retire this profile, we make a sealing with silicone. Okay, we place again, we spread the silicone as a sealing, we place again the profile, and after we place the structural rivets, and you do it structural riveting with the tool. It's the main target of the Sharework project. When it's already rivet, you have protectioning, and after you have a quality check. This process runs 400 rivets per train set for one tramway. Okay. Here I don't see, you will see it way good in internet, the GIF image. Okay. First one, it's the silicone spread. Okay, put in the place. Second place, it's place riveting, fix the aluminum profile. Third one, it's when you apply the tool, you apply the rivet, you break it, and you assemble the parts. And in the fourth, the quality check. Okay. Here, the first one is a bit slow. Here you have the spreading of the silicone. And this process is done in the four corners of the lateral frame. This is only one corner. This will be done in the four corners. Here it's one corner, two corners, three corners, four corners. Okay. What is the critical aspects of doing this task? As I said before, we have a big range of working area. We need a quality check because the structural rivets, it's a special process. Okay. We have high repeatability of process on the riveting, especially, and we have some EHS problems on the riveting tool because it's 5 kilos tool and have a big feedback when the rivets breaks, okay, and high noise, and you do it 6 times or 8 times per corner depending on the assembly, and this is causing ergonomics problems on the operator. Okay, as I said before, it's a special process because it's a structural riveting. The process applying this process, this operation need to be certified. Okay, and you need to make a quality check, check of the operators applying this process. Okay. Why you are trying to motivate and use it automation on the factory and this specific process? First one, reduce ergonomics operators' painful task. Okay. Second one is increase productivity on the assembly line, reduce the times and make more productivity the station. Be the first cobot adoption on production line. It will be the first cobot working on Alstom. Sure, in our site, in other sites, we have other cobots, but not with interaction, I would say. Okay, and it will be a way to certify this special process. It's a structural riveting that can apply in other workstations, not in the same product, but in other products that you're using structural riveting. If you succeed on applying this technology, it can reapply in other processes and other stations. Okay. And the idea is to have a flexibility solution to change to similar processes with low fixed cost to change this solution to another place. Okay. What's the proposed solution? Okay, here it's how we, with our technical partner that in the project it's Eurecat, how we decide to collaborate between the worker and the cobot. Okay. Here it's when the worker works, it's this operation. It's cleaning the assembly areas. Here the cobot spread the silicone, okay, in one of the corners. Sorry, apply the silicone. Operator spread the silicone. Position the riveting, the structural aluminum and the rivets. And after, when it's finished, the robot will go to this corner and make the riveting operation on this corner. This sequence is done in the 4 corners. When the operator leaves one of the corners, the cobot works in this corner, and the operator works in another corner. And when it's finished, the robot apply the cobot operations in the next corner. Okay. Here we have a video. What's the idea of the concept of the operation? Here it's a half of the demonstration, and here how it works. The riveting tool with the cobot applies on the aluminum profiles. Okay. Here it's a proposed solution. Here's current process. Here's the mock-up of half use that you see in the previous video, and here it's the full demonstrator that today it's in Eurecat installation. So I think 2 weeks will be an custom installation to make the final validation. Okay, here it's the full frame. You see it here, the 4 corners, 1, 2, 3, 4, and the cobot in the internal area. The main components used for this proposed solution is a robotic arm. In this case, it's Universal Robots 16G. 2 linear axes, 6 y-axis, the silicone and riveting tool that it's in the head of the cobot, the tracking cameras, Android tablet. The Android tablet, it's used for the interface between the operator and the robot. In normal use, only to start or stop on to resolve problems you're facing, but it's during the process you don't need to use the tablet normally. And after PCs and networks, mainly to manage the robot and the cameras. Okay, how it's the architecture of the hardware that you are using. Okay. And here the description of the technologies and components that have already explained on the project. You have the human task identification. Here you will see how the worker are making some operations and how it's detected by the camera, what it's doing in each one of the movements. Okay, here you are in transportation object. Now the text, we are cleaning the surface. Sorry, I will stop the other videos. Here, spreading silicone is the tech tool. So, pressing again and presetting to position in the rivets and make the riveting with the text. Okay, this human identification. Okay, to organize the work of the robot. Here you have the multi-human tracking, mainly for safety issues and to detect what's the position of the worker to start to work in one corner or not, for example. Okay, this is one of the models that use on this demonstration. Here it's the main process, the riveting. The riveting with the cobot to avoid to have better ergonomics on the process. Okay, here we see it, the positioning of the tool, walk to the rivet and apply autonomously, and this operation is done by the cobot. Okay, and here we have the same for the spread of silicone. Okay, see it here. This is the 2 operations done by the cobot. The other ones, positioning, cleaning, spreading the silicone, is made by the human. And for this, each one of the corners. And thanks, that's the presentation.
Thanks a lot, Jaume, for this presentation. So we hope we will have our final solution in your company soon, during the next weeks. So now we move to our survey, self-assessment question. So what happens when operator place the rivets in one corner and leave the position? So A, the cobot will place the rivets in the opposite corner. B, the cobots rivets in the place leave it by the operator. C, the cobot starts the ceiling. So you can start answering this questionnaire. We have the 30% that are voting already. Okay, let's see if a few more people want to reply. We have 10 seconds more. Okay, so we can close it. So the 80% of the attendees replied B, and the 20% replied C. So do you want to comment something, Thomas?
Correctly, I don't see the screen, but I think it's B. And the cobot works when the place that the worker leave the position and start to riveting. Okay.
Okay. So thanks again for your presentation, and let's move to the third one. So we have again two speakers. We have Pier Vincenzo and Andrea Scala representing Cembre. Cembre is a leading manufacturer of electrical connectors, piping and cutting tools, railroad products, identification and labeling system. Pier Vincenzo will be starting the presentation. He received his master's degree in industrial automation engineer from the University of Brescia in 2020, and he joined Cembre in 2019 as an industrialization engineer. He is in charge of testing machinery control technologies, and is now involved in Sharework project as Andrea Scala, that is a technician in Cembre. He joined Cembre in 2014 as a machine operator, and since 2016 he is in charge of managing all the company's industrial robots by programming and designing new dedicated grips and devices, and also the part of the training of the operators. And they will give us the presentation about human-robot collaboration for workers' assistant in assembly, disassembly, and checking parts. So the floor is yours, guys.
Thank you, Simona. Thank you, Andrea. In the first part, I will show you a short introduction of our use case, giving a brief company overview. As Simona said, Cembre is a leading manufacturer of electrical connectors, crimping and cutting tool, railroad products, identification and labeling system. We have 5 main product types as shown in the slide, and in total we count more or less 60,000 product codes. Extensive know-how in the field of electrical connectors and strong R&D allow Cembre to respond quickly to an increasing demanding market expectation. At the end of 2021, our consolidated sales was more than 166 million euros, with a consolidated net profit of 23.4 million. Cembre is a group that counts more than 800 employees, subdivided into the various plants, also commercial and productive worldwide. And in this context, the Sharework project is placed, and it allows us to develop new challenging technologies for a continuous improvement of our shop floor. To cope with such structured production, a hierarchical control structure is needed, as shown in the picture. This makes ours a flexible machining shop floor that includes horizontal machining, flexible machining systems, lathes, multitasking, grinding, transfer machines, and electrical discharge machining. In our shop floor, thank you, Indra. We can find a complexity of production due to different facts, less time to optimize process parameters, increase the relevance of reusing strategy to shorten time to market, and standardization and modularization of clamping features and cutting tools. These imply an high quality demand for continuous process adaptation that gives the flexibility machining very challenging and allow us to perform a strong evaluation of a human's role in manufacturing. So from machine operators to production supervisors, free time from repetitive and low added value tasks, and increase of operators' welfare and satisfaction. And to conclude the introduction, this slide shows the flexibility dimension that we have to cope. In the shop floor, we count 8,000 machining operations with 50 every hours number of inspection and more than 2,000 number of tool types. We have more or less 4,000 different items with different dimensions and 3 main different materials. In addition, we can find an high variable lot size from 10 to 50,000 pieces with a very different repetitivity and lead time for each item. So this is brief company overview, and then I give the floor to my colleague Andrea to our proposed solution.
Thank you very much, Pierre. I will now show you what we envision is our solution to cope with the challenges of the flexibility we faces every day. So here you can see the layout of our shop floor, our main shop floor, and on the starting from the left, you can see the logistics station, which is a dedicated workplace for operators to work in collaboration with a cobot upside down, and that you can see a robotic cell, a classic robotic cell with an industrial robot. There is a modification, just the first draft of a modification to allow an IGV to deliver single pallets where the work pieces are clamped to the robot, and then the robot has to load it on stone. So pallets and the pieces are locked on predefined and precise position, and then get delivered to the machines and get worked. And logistics station here to the other side of the shop floor, to the robotic cell, the AGVs will deliver parts from one place to the other. See what we have done till now in the project. So the logistics station is installed, and also the robotic cell has been modified, and as well as the tombstone and all the robot grippers and the HV. And now go into details of each area. Starting with the logistics station layout, we decided to build aluminium structure, main structure, and with a table on which we placed roller guides on the single pallets can slide from left to right as a single way roller guides, and there are two positions where the single pallets are clamped and locked, so the operators can work on them, and as well the robots has defined places where to work. And as you can see, there is the cobot mounted upside down on a linear guide, so it can reach every spots that where it needs to work. You also have cameras that can recognize the operators in real time, and thanks to the CNR, the robot is able to avoid the operator in real time because it recognizes where operators. So it can avoid them or stop if they are too close. Here you can see what the first draft of the logistics station HMI. So the operator is able to understand what the system, what the status of the system is. So if in station there is a single pallet or another, what type of workpiece is being delivered to where, so on. Here you can see one of our operators that is doing some testing with in the logistics station, and the single pallets on the designed places to be locked, and he's interacting with a tablet on which there are instructions to follow, and can decide where to work. So if he's working on one station or the other one is for just the robot. So you can see they are both sharing their workspace and working closely. And on the right side of the operator, you can see there is another screen where he can check every time what the cameras are seeing, and if he's been seen by the robot. And the purpose of relocating this area here, so the operators can just focus on their job on inside the space. Thing I want to point out is that the operators were not scared by the robots, so let's say starting to work with robots, especially collaborative robots, but we saw that they're just really curious to start working with something that they see as a new and technologically advanced tool at their disposal. And the only doubts they have is about what will the robot do, but it's just a matter of see what the modification we did at the robotic cell. So we modified the receiving area here for the single pallets using the same roller guides we used in the logistics station. And there is a sliding door that closes the let the robots get out to clamp the single pallets just when it's needed, and safety laser scanners ensures that nobody gets close to the robots while it's moving. Here you can see a close-up of the Thompson with 0-point fixtures and the robot loading and unloading a single picture. Of course, this Thompson it can be used both by and manually by operator. Conclusion. this project is really a solid first step toward a new working method and philosophy, where people are main characters in a shop floors. And as I said before, really looking forward to it because the operators we saw that are not threatened by the robot, and they're really interested in using it instead. And also a dedicated area like the logistics station we designed, sure that it will increase comfort and ergonomics, as well as letting operator focus on becoming production supervisors. That's all from my side. Thank you very much.
Thanks a lot, Andrea, and thanks, Pier Vincenzo, for the session. So I think that you are the most advanced in terms of timings in Sharework, so it's really nice to see that you have already validated the system in the company, but also that you are getting good feedbacks from the operators. We are going to move to the quick questionnaire on chamber. So which is the aim of AGV in the chamber use case? A, lifting a raw part into conveyor belt. B, transporting raw finished pallet from to MCM robotic cell. C, improving the use of pallet truck. So here you have the question. Now we have different answers, so it seems not so clear. Or we can have more than one option. Now we are going to discuss it a bit more in detail. 63% of the people who already voted. Let's give just 5 seconds more. And now we close the questionnaire. Okay, here you have. So the 80% of the attendants replied B, transporting raw finished pallet from 2 MCM robotic cell, and the 20% replied improving the use of pallet truck. Andrea, Pier Vincenzo, if you want to comment.
Yeah, the correct answer is B. The GV has to deliver raw finished pallets from the robotic cell to the logistics station. This way, this is a really low value added task that the operators will not have to do anymore.
Mm-hmm. And the C is completely wrong.
Yeah, the trucks they're manually operated. They're always useful, of course, but they don't interact with AGVs.
Okay, so thanks for the explanation. Now we also move to just a quick survey, and in the meanwhile, we are gonna start our last presentation that will be given by Giuseppe Fogliazza and Filippo Parma from MCM. MCM is supporting the integration of machine and accessories technologies and develops production supervision and planning software, and also provide process technologies. And so I kindly ask you, Giuseppe and Filippo, to open your camera and to join me to the session. Giuseppe graduated in Pisa in information science in 1986, and he started the collaboration with MCM, that is a company located in close to Piacenza. And since 2014, he has been the director of Machine Center Engineering in the software division of MCM. He has been responsible of the relationships with academia and other research organizations, and this is how also we ended up with this European project, but they are also working with national and regional ones. And since 1997, he is a member of SIRP, And in 2014, he has been a member of the management and control body of the Scientific Technical Committee of the National Technological Center. And also we have with us Filippo Parma, that is a mechanical engineer from MCM. He got a bachelor degree from the Polytechnic of Milano, and he graduated in Parma in 2019 with a master degree in mechanical engineer. And he has been carried out the R&D thesis in the industry in CIDL, with the topic about development of robot gripper and aseptic environment. He has been collaborating in different kind of European projects, and since November 2021, he's working in the development of customer projects. And so I'm really glad to give you the floor for this presentation related to redesigning logistic flow in the shop floor through collaborative automation.
Thank you, Simona. Hi, everybody. Here we are, and I am Giuseppe Fogliazza, and together with my colleague Filippo Parma, we would like to show one potential field for the application of the technologies developed inside Sharework. In this section of the workshop, we would like to put in a perspective the technologies developed, enlarging a little bit the context from cobot to collaborative automation and human-centered manufacturing, and how these two topics have the potential to modify the scenarios of flexible mechanical workshop. And this evolution is in a strict relation with the new requirement for product, process, and production system. So let's start. We introduce some of the actual trend in the field. Some of them already comes out, like the figures that you see on the screen that are coming from Cembre. That is an example of flexible machining with a very deep requirement. It's a long time that in manufacturing there is a constant pressure on the products towards extensive customization that lead to a reduction of the overall product life cycle and reduction in volumes as well. So even if the Cembre scenario is already qualified as an extreme flexible machining scenario, things are going worse every year and demanding to explore new ways to cope with flexibility. And the product evolution requires evolution also on process development, requiring effort to reduce time to market and to reduce the scraps during production. For time to market, this means an extensive usage of digitalization and simulation, but also the capacity to reuse knowledge from previous projects in the development of new machining process. For scrap reduction, this has led during the years to enhanced sensorization and better control process procedure, but also the integration of control measuring machine in the standard routing of manufacturing parts, as well as the capacity to feedback from measure to process. And one interesting point, the capacity to rework incorrect features. On production systems, the need to increase productivity by reducing production cost has long led to the introduction of increasingly standard levels of automation in order to exploit unattended shift. This trend has become even more evident with the recent evolution of the global market, characterized by an increase in personal costs and crossed by phenomena like reshoring or friendshoring that is affecting Western and especially European manufacturing. The push toward automation, even in flexible production context, is also redesigning the relationship between man and machine. We already have heard the term evolution from machine operator to production supervisor. and this will be something that we have to take in consideration, as well as the aspects that are creating relevant requirement in modern manufacturing toward a sustainable and human-friendly working environment. In addition to safety, which can never be called into question, there are other aspects that are emerging. Above all, the enhancement of the role of human personnel in the workshop. From machine operator to production supervisor means to have a division of tasks between machinery and personnel that assign to the latter activities with high added value, able to stimulate and to use human cognitive abilities. This is one of the state-of-art flexible manufacturing systems that my company have developed, and that integrate multiple processes, take the operator far from the machine and make them really supervisor of the production with the capacity to be supported by highly informative interfaces. And this level of integration is achievable only focusing the flexibility of the system. That is limiting the flexibility to a specific family of products. This system are built using traditional automation, and this led to a certain number of drawbacks, especially when a new process needed to be integrated or volume needed to be extended. So we do not have, with the traditional automation, a general solution for to integrate multiple processes and the capacity to reconfigure and to adapt continuously to the modification of production requirements. But what if we are capable to manage individual parts? This seems a promising path for a generalized capability for a flexible machine. The state-of-art industrialization in machining requires dedicated multi-clamping pallets. And there are very good reasons related to productivity to have this industrialization. Since a long time, this approach is hampered by the degree of complexity in the process development and de facto impossibility to partial rework of feature not in tolerance, because the part need to be unclamped to move to the control area and then reclamped, and this creates disturbances in the process, not compatible with maintaining tolerances. But if we are capable to manage individual parts, but we can simplify the overall machining process, building it from a reusable individual entity. And when control fails on a specific feature, we should have the opportunity to rework it. And this will reduce time to market and potential scrap. So very in line with the original requirement and important requirements that are crossing this sector. But in order to achieve this, we need the support of two major advancements in machining. The first one is a new approach to the development and execution of the machining process, named network part program. It was derived from research activities on the evolution of the ISO programming language 6983 that is used to program machine tools since the 50s of the last century. Even if the new emerged standard, that is the ISO 14649, commonly known as STEP and C, never entered in industry due to the opposition by the two CNC market leaders, Siemens and Fanuc. Nevertheless, the concepts behind found a way to reach the market thanks to the network part program initiative. It enables the creation of a work plan for a single part from reusable building block, named machining operation. Then these individual processes can be aggregated in opportunistic combination of the same, as in the picture, or different parts using multi-clamping pallets. So The multi-clamping pallets saturate the machining centers area and then can be executed in an optimal way thanks to the network program executor. But this offers the possibility to selectively execute or re-execute a subset of this working step. The other advancement is the introduction and widespread use of modular tooling that can be grouped on multi-clamping pallets using the standardized zero-point attachment. This offers a general way of integrate different processes from the machining part on machine tool to the control on CMM, and hence eliminate the main obstacle to rework that need to unclamp and reclamp the part. A managed flow of pre-clamped parts along the various stations of the machining process open new possibility to design modern shop floor. Another key aspect of the new proposed approach is related to the role of human in a machining shop floor. To support the inevitable transition from machines operator to production supervisor, it is necessary that the human activities concentrate on high-value tasks, related mostly to control and validation of the machine feature. We had examples during the previous presentation of the possibilities to introduce collaborative automation to relieve human from low-value tasks. But I want to point out the attention to the risk that is needed to mitigate in very flexible production context. So many sources of information put a lot of pressure and require cognitive effort and the risk of information overload. In particular, it is very important to provide clean interface to inform operators about the task under execution. But even more important is the capacity to make evident the behavior of the artificial autonomous part. In the field of operator instruction, we started from paper instruction associated to the part and went through paperless shop floor where documents are on screen. Now the tendency is to details preparation and control task, presenting details of the procedure to execute on computer interface that enable interaction with individual procedural steps. The future is associated to the development of robotic partners with interface to share not only the working space, but also awareness between human and artificial agents of the current situation related to the task to perform. So, for this point, in a world, we want to create an environment where operator can understand machines' behavior and machines are capable to adapt to the behavior of humans. This is an important aspect of collaborative automation. The possibility to define explicit models of the activities that take place in the shop floor, process handling and control, and to interact with them at runtime is one important technology to support this vision. Another key aspect is related to the capacity the development of advanced control techniques capable to recognize human behavior and generate proper trajectories for robotic arms or automated vehicles adapted to the presence of human parts. In general, it is necessary to cope with uncertainty in the control decision. To this extent, there are many sources of uncertainty in a collaborative scenario, starting from uncontrollability of the human agent that lead to continuous adaptation of the behavior of the autonomous agent, and as a consequence to the reduced capacity to estimate and predict duration of individual activities. And this uncertainty moves upward along the hierarchical levels of the control system, making the task of planning and controlling the execution of plans more complex. So in Sharework, we have introduced a planning and scheduling technology based on timelines that has two major advantages. The first is the capacity to work on a hierarchical description at different level of abstraction, and hence matching the layered architecture of a manufacturing shop floor. The second aspect is the integration of planning and execution, relying on the same semantics of timelines. If this is of paramount relevance to the dynamical adaptation of autonomous agent behavior to the environment. This part of this environment are uncontrollable humans, but also other autonomous agents committed to the execution of different goals. This offers to the collaborative automation approach not only a pillar to build a real cooperation between human and robot, but also create the basis to ease reconfiguration and required adaptation in the interaction between independent, autonomous, artificial agents. So, putting all things together, we finally arrived to the vision that we already was presented inside the Chamber use case. Chamber has developed a long-term vision based on a simple but powerful concept to transform the whole shop floor in an integrated, flexible manufacturing system. People will move inside this manufacturing system, sharing the space with automation devices and cooperating with artificial and autonomous agents to pursue production goals. Complex activities with high human content will be centralized and moved far from machine in workplaces more comfortable and ergonomics and supported by robotic partners for low-value activities. Inside this environment, a flow of pre-clamped parts assembled at a collaborative logistics station are moved around to be processed according to routing instructions. And this entire shop floor will be controlled by a control system that is hierarchical by nature. And inside the Sharework, we have developed the integration of the control of the logistic work area, the integration of the AGV fleet manager, and the integration of the controller of the existing machining work area. Then we have developed a simulation model of the shop floor to validate the overall solution and to estimate how performance indicators are affected by different elements. Now I leave the floor to Filippo for a brief description of his work in the development of this simulation.
So, good morning, everyone, and thank you, Giuseppe and Simona, for the introduction. So, let's start talking about this new perspective of redesigning industrial workshop. In this vision, it was introduced the control system to manage logistical flows in the shop floor. The control system will have to command different production units and different priorities of processing tasks, and consequently different priority of handling materials, with a view to managing small production batches, but with a large variable of product. It became essential to foresee possible logistical criticalities, to reduce the lead time, and to optimize saturation of the production units. This is the purpose of the discrete event simulation shown here. For this demonstration, it was virtually remodeled the manufacturing facility of the Sharework use case. Layout here presented shows the units directly involved in the Sharework project, such as logistics stations and the fleet of AGV, as well as all the production units already installed and working at the Sharework facility. The flyover of the video wants to clarify the meaning of the production units involved in the Sharework plant. The model allows you to perform multiple what-if analysis, simulating different production scenarios. Depending on the scenario,
to be simulated, it is possible to define the input and the output of the system, such as throughput rate of the code to be processed, saturation of each production unit, number of AGVs to be allocated for each mission, the heat map, runtime of the AGV path, and all the variables that directly depend on the units involved in the simulation model. In conclusion, the possibility of scenario are so many. The simulation model is placed as a support tool to control system in the evaluation of the best decision to be taken in the medium short term. So this is our project. I leave the floor to Giuseppe for the conclusion.
Thank you.
And,
thank you. Thank you very much. So some final words. We were the only one that we didn't take the correct timing. Sorry for this, but implementation of a logistic flow of individual parts is the basis for a generalized approach to transform a machining shop floor in a flexible and integrated manufacturing system. We have shown some of the required advancement of the current industrial practice. Moreover, it is a promising context to support the evolution of the role of humans in manufacturing. One of the key problems to solve is the increased complexity and the injection of uncertainty in the coordination of multiple autonomous agents. For this reason, one of the main topics of research activities for us will be related to the development of a reactive planning module at shop floor level. Thank you for your attention.
Thanks a lot, Giuseppe and Filippo, for the presentation. Since we are a bit late, we will just move to the questionnaire and the survey, and then to the question and answer session to see if we get any of them. So here the questionnaire, what are the main drawbacks of the single part management approach using the current technology? A, production inefficiency, B, management complexity. Both A and B are correct. %63% of the people voted. 10 seconds more. Okay, so we can close the survey. Yeah, so here the answer.
I expect this answer. I have doubt by myself. The one that gives the question. I know that the most correct it could be both A and B, but nevertheless, I do not underline actual management complexity. So I think that. It's a good. The attendance was putting attention to what I said. So thank you very much.
Yeah. Thanks a lot, Giuseppe. I mean, it's crazy how many things you have to take into account apart from the technical aspects. Also, you know, the position and also people that can move.
I try to pack a lot of concepts.
Yeah. So we are also moving to our last questionnaire, and in the meanwhile, I'm also asking to all the speakers to open the camera because we are going to discuss a bit more about a few topics, and we have also the question and answer session. So if there is anyone that from the attendees that want to interact with us, just raise your hand. And the organizer will give you the permission to speak, or if you are a bit shy, you can just drop the question in the box. Okay. We are still waiting for a few. So I would like to start just with a more general question to all the industrial partners. So in general, how would you say, which are the benefits for operators and which are the benefits of the businesses when we are speaking about collaborative robotics? So I don't know if there is anyone that would like to start with a quick answer.
Yes, but I try to focus all my presentation on these two aspects. And I think that what is coming out is a new way to proceed with automation for manufacturing. A different approach. Since now we have concentrated in automated all we can, and then when we are no more able, we let the people to enter in the picture. This should change. We should start from enhancing the value of the work of people, trying to keep out from them low value tasks. And this is completely different. And also for the flexibility that this new automation can provide, this is a very promising to have for the reconfiguration aspect that will become more and more important in our shop floor.
Mm-hmm. Thanks, Giuseppe, for starting the discussion. I don't know if there is anyone else that would like to interact.
If you want, Tom. For us, it's ergonomics, I think, as other end users. I think it's one of the improvements.
Mm-hmm. So I see that also Mikkel is
Yes,
agreeing.
from our side, I agree with Jaume. Mm-hmm.
So it's somehow the operator's condition. And yeah, I have a question for Chambre, because you said that your operators are not threatened by the robots. What do you think? This can be extrapolated universally, or it's just because your operators are really proactive and are keen to have new technologies in Chambre?
You are asking me a really difficult question, you know, and of course I cannot say, cannot know it, but I think generally speaking, humans are really curious, especially to learn new things, and you don't know the machine it's in front of you. You're a bit not scared, but cautious, I would say, to use it. But when there is someone that teaches you how to use it properly, you're not scared anymore, and you're just want to see how well it works, if it suits your needs or not. So it's really important to develop a solution, an automation solution that fits the needs of operators, of people, first of all.
Okay, thanks, Andrea. So it seems that at least the use is not a threat for the project anymore, at least from Chambre. And also, yeah, related to it, yeah, I know, Mikkel, you were speaking before, that one of your issues is that you have a lot of sick leaves because of this repetitive task that needs both strength and precision and so on. So what is the injury rate due to bad ergonomics in assembly?
Yes, that's one of our problems. And for example, last year from 8 operators, we had 3 injuries, so 3 sick leaves. 3 sick leaves from 8, so almost the half. Yes, that's why we need to improve the ergonomics of the operator, something critical.
Yeah, and also we have been discussing, yeah, during the project that also for gender equality will be also really useful in order to have more female, but also inclusion in general, not just of gender. It would be obviously a good point to have collaborative robotics. And yeah, in that sense, yeah, I see that Seat is not here anymore. So to Chamber again, why so important to combine a flexible machining system with a high production variability?
The gap between a fully automated environment and shop floor, there is this need to flexible, as more flexible as possible. So this kind of collaborative automation really helps us in this scenario, in this case.
Thanks again, Andrea. And yeah, then we have a question for Giuseppe. So how do you imagine to apply the Sharework module for task planning in the context of management of logistic flow in the shop floor level?
Yes, there was a slide that I have to cross a little bit fast related to the organization of the overall control of the shop floor. If the shop floor need to be integrated and fully automated following the collaborative automation approach, we need to integrate at the higher level of the hierarchy planning and execution system that is similar to the planning task inside the logistics station. For this reason, we are looking at the timeline method, as a promising way to develop a reactive planner for the entire shop floor. Because in this case, you have uncertainty. That is not the way that we are using today to develop our planning system. So this is the challenge for the next period.
Really good point. And then also a question for Jaume. So what are the next steps for the cobots application on special processes?
Yeah, okay. Our demonstrator today is based on structural riveting, but in our roadmap, this is the first point to apply after in other special processes that can be gluing or thickening, as the demonstrator of Goisper, and electrical clamping. And this is the 4 special processes we are look for work afterwards this project and in the next years.
Thanks a lot. We have also a question, a more general question, philosophical question. Francesca, maybe you can take it. From an ethic perspective, human-robot collaboration is better than replace humans by robots?
Yes, I think I can answer. Yes, it is better from an ethic point of view, because while with fully automated production lines, the robot replaced the humans operator. With collaborative robotics, the operator is not replaced by the robot, but the operator collaborates with the robot, so they work together, and the operator is required for his skills, like with his cognitive capabilities, and his human skills are required. So in collaborative scenarios, the operator is not replaced by the robot.
Okay, anyone else want to comment on that?
Yes, but I think that also for the business is better. Also for the business is better because it's only from joint competencies from automation and from human we can have better production that costs less less error, less scrap, and is on these business goals that we have to concentrate to demonstrate that the approach is sound also from the economical point of view.
Yeah, and do you think that the operator skills that will be needed in the future to interact with robots are different from the skills that you are requiring now from human resources perspective? So
you asked,
do you?
I missed
yeah, in general, yeah. I was asking in general, yeah.
It's an easy yes. An easy yes. But in general, there is the need of new skills from people working in manufacturing because they are doing a different job. We said since yesterday they were machine operator. They are serving the machine for all the things that the machine was not capable to do. And changing this is of paramount relevance to justify the high cost of personnel and to attract people in manufacturing. And so, as is of paramount relevance, to provide to them a more clean, less noisy, and safer place to work.
Okay, then. So, if you don't have anything else to add, I think we have already past the time. So I would like to thank you all for being here. I know you have done a big effort because you are all working hard in Sharework during these days. So thanks a lot for this session and also to the attendees for being here with us. Unfortunately, this is the last training session, so I'm sure that if you want to get a bit more insights, you will find it in YouTube. The recorded version of all the session we had. And on the other side, you will get the final survey by email. So we kindly ask you to reply to it because it will be really useful to improve our session during the next years. So thanks a lot to all of you and see you soon.
Bye.
Bye bye.
Thank you.
Bye.
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 Bye bye.